All right, hi everybody, welcome back. The topic of the day here is heteroskedasticity and how to fix it, right? So last time we took a look at an example data set, went through some of the basic commonly used techniques of how to test for the presence of a heteroskedastic error. We want to kind of pick up where we left off with that same data set, the same regression, and look at some of the common, again, basic ways of dealing with it. How to get usable, valid hypothesis testing results in the presence of a heteroskedastic error. So let's go ahead and take a look. We'll kind of start from scratch here real quick. If you recall, we were using a simple wage determination model using that Jeffrey Wooldridge data set from the Boston College little data page that we can just call that up here. So we use that command bcuse once it's installed, and the data set we were playing with was that wage 1 data set. And if I recall, we were looking at something like this. We had wage as a function of the level of education of the individual, the level of work experience, and then we were including a gender dummy variable. So female equal to 1, the individual is female 0. Otherwise, and once again, every time I open up Stata for the first time, it seems to be really slow picking up. While we're waiting for it here, just as a quick note, I'm using a Stata 15, the SE version. All of the commands, all the techniques we're talking about here can be applied to any version of Stata. And okay, enough pattern. Here we go. It's caught up to me here. So if you recall, we had kind of our expected levels of significance, the expected magnitudes and signs of the coefficients. Everything looked good, but when we dug a little bit deeper, specifically when we applied that Bruce-Pagan heteroskedasticity test, where we ran that post-estimation command het test, we included all of our right-hand side variables, and we asked Stata to call this up as an F statistic for joint significance. We found highly significant heteroskedasticity. So those right-hand side variables are jointly significant in predicting variation in our squared residual. So that's where we left off last time. Now, imagine yourself, again, you're a researcher in this position. We really want to run this model. We want to get results. We know we can't trust these t-statistics at this point because of the heteroskedastic error. We basically have two kind of philosophical approaches to take at this point. One is, well, we can re-specify the entire model to give ourselves new error terms that will be homoskedastic, right? Then we'll get those trustworthy, valid hypothesis testing results. The other way to look at it is just to recall that kind of the damage of heteroskedasticity is really isolated in that variance, standard error, and t-statistic, right? But it doesn't cause inconsistency or bias in the coefficients. So maybe the minimally invasive approach, right, is to leave the model alone, but just recalculate the variance of the coefficients, thus the standard error, thus the t-statistic, in a way that doesn't require, that doesn't assume homoskedasticity, right? Of course, that's the robust standard error approach. So that'll be the last thing that we take a look at. One way to start this is to think about re-specifying your model by applying the appropriate nonlinear transformations. Right? You could take a look at the full discussion of that in one of my previous videos. But one of the things we talked about was when we use a log transformation to linearize a model, one of the ways to think about what that's doing, right, is it's decreasing the dispersion of your y variable at large values, right? Taking that nonlinear log transformation. Well, if that's happening to the y variable, it's happening to the residuals as well. And when we think about the typical heteroskedasticity case, it means as the values increase, the dispersions increase as well. So it turns out applying a log transformation can have a side benefit of mitigating heteroskedasticity. Right? So if you recall, we have kind of the natural log version of wage already created in my data set here. So we can just rerun my regression here, but with, instead of wage, L wage. Again, that's just the natural log of each observation of an hourly wage. We won't apply what would probably be actually called for, which would be a polynomial transformation on the right-hand side, but we'll just leave education, work experience, and of course the female dummy variable alone. And let's recall up that post-estimation Bruce-Pagan test. And wow, in this case, that was pretty easy, right? It turned out doing what we should have already done, applying the linearization, applying that log transformation, also seems to fix that heteroskedasticity problem. We still have, it's borderline significance, joint significance in that Bruce-Pagan test here at 20%. We probably want to explore that a little bit more, go through the entire testing regimen to make sure that we're safe there. But that certainly seemed to fix things. But that's not very interesting, right? So imagine we didn't do that, or imagine that didn't work, and we were back in that linear model. What else do we have at our disposal? Well, the primary respecification, right, is that weighted least squares approach, whereby we obviously weight each term in our equation, our y variable, our x variables, and most importantly, our error terms, by the assumed driving force of that heteroskedasticity. Right? So we're not going to go through the full derivation here, but just real quick, taking a look. There we go. And what we're going to do here, if this is our original model here with our, sorry, let me bring up my little pen. With wage as a function of education, experience, female, and there's the problem, our error term, which is heteroskedastic. Well, what this weighted least squares approach is going to require is a known functional form for that heteroskedasticity, right? So it's not just enough to say that the variance of ui is equal to sigma squared I, so it varies by individual, which is the definition of heteroskedasticity, right? We have to then say, well, it's actually heteroskedasticity following this specific functional form, that underneath it all there is this constant error variance sigma squared that is scaled up or down by some variable. So obviously I'm positing here the possibility that the driving force behind our heteroskedasticity is this level of education, right? That seemed to be one of the takeaways from our testing from the last video, that there was a significant positive relationship between education level and error variance. So let's imagine that's our assumed functional form. What can we do about that? Well, what that tells us is that if we take the variance of a weighted error term, specifically weighted by the square root of this driving force, whatever variable, whatever function is scaling up or down that sigma squared. So if our new variance is instead of ui, it's ui divided by root education, well, we apply our variance operator, right? And if we assume that education is a fixed value, right? It's a truly exogenous value, which that's a whole nother video, but let's take that for granted at this point. By applying that, the mathematical variance operator, right? We pull out any product term from within the variance operator, and we square it, right? So we take out 1 over root education and square it, and we're multiplying by the variance of ui. Well, what is the variance of ui? It's sigma squared I. But what is sigma squared I? By assumption, here it's sigma squared times education, and look at that. I'm surprised every time it works out. Education cancels out, and what do we have? We have a constant error variance. Seems easy enough, right? So what that means is our regression equation has to be changed across the board, right? Keep in mind, the whole point of this is to get a new error term, but we can't just transform the error term. We have to transform the entire equation. So we need a new left-hand side variable. Instead of wage by individual, it's wage divided by the square root of education. Instead of education, it's education divided by its own square root, which I know is just the square root. Same thing, experience divided by square root of education, and then maybe least sensibly on the face of it, of all of them, is that female 0, 1 dummy variable, again, divided by the square root of education, right? So of course, the first time you see this, if somebody just shows you this equation, you would say, what are you doing, right? You're looking at their variables and saying, why are you taking somebody's work experience, dividing it by the square root of the number of years of education that they have? That makes no sense. And it really doesn't make any sense. But it gives us this error term. Right, so note that the role that the coefficients, the structural coefficients play in our equation, they don't change, right? So we're still going to be able to interpret that as partial wage, partial education, partial wage, partial experience, partial wage, or the intercept shifting effect of that female dummy variable, right? So this seems like a lot of work. We also have to adjust what would normally be our intercept. It's actually going to be a coefficient on this 1 over square root education term. Again, you're going to want to look more closely at the theory behind this, right? But basically the idea is once we decide on a factor here, we just divide everything by its square root, right? So this could be the log of education. We divide through by square root log of education. This could be education squared. We divide through by education. It could be obviously a totally different variable. Whatever we choose there, we divide through by its square root. Okay, so now we just have to do this in Stata. And let's get rid of that, sorry. And let's go back to Stata. So this is a little bit tedious, unlike the rest of the video, right? How would you tell the difference? This is the tedious part of the video, I'm just telling you, that we're gonna go ahead and generate these variables, right? So let's generate what we'll call our weighted wage variable, so wage underscore W. Call it whatever you want, that seems to work. And it's just going to be wage divided by education to the power 0.5. Again, on the face of it, doesn't make a whole lot of sense, but we know what the true end result is going to be, right? Then do the same thing for our x variable, so education divided by its own square root. Just keep the pattern going there. Work experience. Let's get that weighted experience variable. And again, so turning our 0, 1 dummy variable, it's going to go from 0, 1 to 0, 1 over root education. Right? So this is going to be the dummy variable weighted. And then lastly, we need that new intercept term, right? So there really is no constant. So I'll call this our B0 underscore W. Whew. Now all we have to do is run our regression again. And let's go back up and call up our OLS model. Let's get rid of the L. We're not doing the log here. And we're just appending each of our variables here to call up those newly created weighted terms. But we're still just running it with our OLS regress command in Stata. Right. So, again, everything looks pretty much like it should. The coefficients change a little bit, not drastically here, so we still have our positive significant coefficients on education and experience, and again, the unfortunate negative significant coefficient on that dummy variable. So, now we want to know if this actually worked, right? So, of course, we know what to do. We apply our testing regimen to this weighted least squares regression, and it's kind of a trial and error process. And if you're thinking, well, okay, if every time I have to run this, I have to regenerate new weighted versions of all of my variables, that sounds like a huge pain. It would be. But of course, Stata has us covered, right? So there's a command that we can call up here. Let's go back to our original regression and get rid of the log here. We can run it with just the regress with our regular variables, and Stata will do the weighting for us. So in brackets, not parentheses, but brackets, we call it this analytical weight function. So AW, and what is that weight going to be? It's going to be 1 over education. Right? So I know we divided everything by the square root of education, but this is the term that actually goes into the variance, right? So the assumption of the variance is that it's divided by the level of education. So if we plug in AW equals 1 over education, Stata should go ahead and do that 1 over square root for us, okay? So what should happen is that we'll get the same coefficients that we just did with our created variables. Oh, no, we won't. Sorry about that. Just realized I forgot a major component here. Let's go back up. Sorry, to the regression that I just ran. Note what we did here is I forgot to include the weighted constant, right? So I need to put in the B0 underscore weight and then the option no constant. Maybe I'll edit that mistake out later. And this will be the one that Stata is going to replicate. Okay? So again, we still have the magnitudes changed a little bit, but this is going to be what we actually should see. So let's go back yet again and go to the unweighted versions of all of our variables here. And now we'll apply that analytical weight. So AW here equals 1 over education into bracket. And now we see here was the one we did by hand. Here's the one we did with the Stata analytical weight. So obviously, if you had the choice and you had to do this as part of a trial and error process, this is the methodology you're going to want to do, right? So what do we have to do at this point? Well, we can just call up, again, that het test command and see how we did, right? So het test, and we'll do it the same way we did before. There's other varieties. Of course, we'll just apply that right-hand side and F statistic set of options. And look at that. That did not help at all. It was a good try, though. So somewhat surprisingly, using education as a weight doesn't seem to work. But this would be basically telling us our assumed functional form was incorrect. Maybe we had the wrong variable. Maybe we had the wrong functional form of that variable. But it becomes real easy now to try different variations, right? So what if it really was education, but we had the wrong functional form? What if instead of dividing by the square root of education, we should just be dividing by education itself? So we put in the square into our analytical weight. We rerun the model. Again, qualitatively, the coefficients aren't changing here. And then we rerun the test, and it actually got worse, right? The F statistic is getting actually bigger here. So maybe we're on the wrong track altogether. What if it's one of our other variables? What if it's work experience that's driving the heteroskedasticity? Let's test for that. Nope, that didn't work either. What if it's job tenure, how long you've been at the same job? Surprisingly, that actually helps, right? We may be on the right track here. So then we put in a square term. We run it, no, not quite. You see what we're going to run into here, right? So this weighted least squares approach is very much a trial and error process. You can narrow it down using our testing procedures, but you really have to hit on exactly the right variable in the right form. There is what's called a feasible weighted least squares approach, where we estimate the optimal function to put in that weighted term. That'll be something we'll hold off on exploring. So imagine you find yourself in this position, right? You think you know what's causing it, you try a bunch of different options in weighted least squares and nothing works. Do we have to just throw away our regression? No, we have that other option in our back pocket, that robust standard error calculation, right? So, what is that robust standard error calculation going to do for us? Let's go back to our slides. So, there's way more to it than this. We just want to look at what Stata is going to do for us. In the simple linear regression model, again, with only one x variable, just so we can see what's happening, our calculated standard error of our b hat coefficient, right, is that square root of the estimated variance, so the square root of our sigma squared over sum x minus x bar squared. Obviously, that's going to assume a constant variance, that we have this constant sigma squared. If we can't rely on that assumption, we basically rederive the variance of the standard error without applying that homoskedasticity assumption. This is as far as we can get in our derivation process, right? So in the numerator here, rather than just that lone sigma squared, that constant value, it's going to be our sum x minus x bar squared times what we know to be our proxy, our estimator for the individual observation error variance, the squared residual. So again, it's more complicated than this. It's probably easier to see it with the error variance covariance matrix, but just to get a feel for it, this is basically the change that Stata is going to be doing for us. And always our friend, Stata makes it really, really easy. Right? So all we have to do is go back to our original model, no analytical weights, no transformations, and at the end of it we go comma robust. And so the default here is that's going to give us the white heteroskedasticity robust standard errors. Right? And so let's go ahead and call that up, and we notice a couple things, right? Again, qualitatively in this case we don't have any changes. Our coefficients are identical, and the levels of significance are also identical. We also note that there's a big missing patch of information up here. Well, if you recall, in the standard Stata output, you see our sum of squares, right? Our residual sum of squares, model sum of squares, total sum of squares, and their mean sum of square components. To the best of my knowledge, Stata omits that information when we use the robust option, not because it can't calculate it, but I think it's just as a reminder to us that we shouldn't be using those numbers to calculate things like F statistics, right? We would need to do a robust F statistic. So anything you're doing by hand, you really shouldn't be using those numbers. I think they should trust us and just put the numbers there, and we would know what to do and what not to do with them. But I think that's what's happening. Correct me if I'm wrong in the comments. So a nice way to kind of round this out is to just show kind of a side-by-side comparison between the robust standard error results and what the kind of the standard OLS output gave us, right? So a nice way to do this, and I'll do actually a full video on this later on, I got lots of time on my hands, is to use the estimate store and estimate out option. So ESTSTO robust. So this command stores the estimates from our most recent regression, and it stores everything under the name that we call up. And I'm just going to call it robust as opposed to our standard OLS. Right? So that puts it into Stata's memory. And let's go back and re-estimate them all without the robust option. ESTSTO OLS, right? So no adjustment, our standard OLS. And then we can use the ESTOUT est out option, and the standard default just puts the coefficients, so the beta hats next to each other. And that's gives us some information here, exactly what we expect, right? The coefficients are identical. The robust standard error calculation, unlike the weighted least squares, doesn't tinker with the x variables and the y variables or the coefficient estimate. So those are all the same. Where the differences are, again, in the variance, standard error, t-statistics, and p-values. So with this ESTOUT option, let's go ahead and, so we'll call up, in this case it's the only ones we have, but you would call up the names of the coefficient vectors, the output that we've saved, so robust OLS, and then we want some specific information called up. So we use the option cells, and we want the coefficient estimates, the beta hat, so that's going to be B. And then in parentheses next to that, we're going to put the word star, which will give us 1 asterisk for 10% significance, 2 for 5, 3 for 1, and none for not 10% significance. And then let's also call up the standard error, so all in those parentheses. Now we got something in a nice, convenient little table here. So say for education, the coefficients are identical, but the robust standard error is a little bit larger. This is typical, right? It's not mathematically guaranteed, but it's the typical result. We get an efficiency loss, typically, in our robust calculation, right? For experience, it actually comes down a little bit, and, oh, look at that, for female as well. So this is what we would call a zero-cost option, right? We don't lose anything in qualitative results. Everything that was significant at 1%, which was all 3 variables, is still significant at 1%, and you don't have to know the specific functional form of the heteroskedasticity to get results that will be valid with this robust standard error. the hypothetical gain from the doing all the trouble of the weighted least squares is that you can get pretty meaningful efficiency gains if you get the right functional form. So you might find yourself in a position where you're not sure which direction to go, and you might have to do some further exploration. Right? But that'll be enough to get you started. So, as always, leave a comment if you have any questions or you have a suggestion for another topic that we could look into, and I will see you next time. Thanks.